So the third one is mineral egg solution or solvers, mineral egg solution. So some minerals are happy being mixed together at high temperatures, but separate as they cool, as they glue together. Similar to how oil and vinegar separates in the fridge, meaning that when they cool down, they go their separate way. But when the temperature is high, they mix up. So by looking at this composition of these separated phases, like those found in feldspar, we can determine the temperature at which the separation occur. So when something is cooled, when you see it mixed together, you know that when you see it mixed together, that shows that that thing is occur at very low, it formed at low temperature. But when it's separated, you know that it formed at high temperature. So applications of this geothermometry. So like I said before, it's not just about isn't about lab exercise. It's how we build thermal history of the planet, the thermal history of how mountains were built. We can track how hot mountain belts got during their creation, meaning that the mountain we see now, what was the temperature during formation? Magma generation, it helps us to understand the exact depth and temperature where magma is born. Metamorphism, it allows us to constrain the extreme pressure and temperature condition that transform one rock type to you know what metamorphism is. When the rock forms from one to the other, they metamorphosize, change this to pressure, temperature, and all that. So this is a schematic to further illustrate this garnet and just for pictorial purpose anyway. So inclined estimation example 2. Do you have example 1? Okay, this is example 1. Okay, example 2. Radiogenic heat production. Granitic crust is enriched in heat producing elements. Estimate the heat production rates for a typical granite. So we have average concentration of uranium, thorium, and also potassium. And heat production constant. We have this granite density. We have this. So the task is to estimate the production rate, which has been estimated here. Now, for better clarification, I believe I decided to make it one after the other. What was the answer? Okay, 290. Okay, 390, sorry. Let me say again. 390. All right. So now, these are the items, these are our data, and convert K to ppm of elements. So let's go through it one by one now. So this example 2, let me put it that this example 2. Okay. So this explains how much heat is generated by a piece of granite. Simply through the radioactive decay of elements within it. Think of this like calculating the internal heater power of the Earth's crust. So the granite is a primary rock type of the continental crust. Unlike the mantle, granite is enriched with heat-producing elements. The three big ones are uranium, thorium, and potassium. The goal is to find A, the production rate, the radiogenic production rate. Measure the measure in microwatts. Let me confirm this. Just a moment. I want to confirm something. Okay. Microwatt per cubic meter. The variables, that's the ingredients. To solve this, we need three types of data. Concentration, how much of each element in the rock or is in the rock, how much of it? Measured in ppm, parts per million, or in percentage, in anyone. Each production constant, H, how much heat or how much energy does 1 kg of the specific element release? The density, how much does a cubic meter of granite weigh? So this is a standard. So 2,700 kilogram per meter cube. The first thing you do, so first of all, because you can't add percentage to ppm, 4% of potassium is the same as 40,000 ppm. Since 1% equals 1,000 ppm. In decimal form, for calculation, 4% is 0.04. Step B, calculate the heat per kilogram. We multiply the concentration of each. You can see this is just the solution. And that's why most times when I give a question and I will explain the solution at times could be very funny. Although some solution might be a bit complex anyway. So if they are too complex, I try to solve it again. So from the example I've given you, your job is find the solutions. I've given you a broad. Some are straightforward, some are not, and I know that. So I'm not. My job is not it's not always to give you everything you just need, like a primary school teacher that is teaching primary. Also do your small research, but I will give you as much information like you need. So the concentration is not making noise. Akinola, mute yourself. Oh, I think I've muted yourself. Okay, so we multiply the concentration of each element by specific heat constant. (9.7 micro this. You can see 9.7. That's where we got that times 4 kilogram. The same thing with thorium and all that. So the sum, when you add this up, the total is produced by 1 kg of the granite is roughly this. Then step 2, convert to volume. Since 1 the heat per cubic meter, We multiply the heat per kilogram by the density. Density, we have the density of this times this value, we have this. What again do I need to say? Um, just a moment. I'm just checking something out. Um, okay. So what is the implication of this? The results might seem small because of this micro, but compare it to the Earth's mantle, which only produce about 0.02 Hz. Even though the continental crust is very thin compared to the rest of the planet, it is so concentrated with radioactive elements that it creates a massive amount of the heat we measure at the surface. It's effectively a radioactive blanket keeping the Earth or the planet warm. So the ground unification from heat flow to mantle convection, forming, causing plate tectonic. Heat flow, it now causes mantle to transfer of heat in liquid form, which results to what we see as plate tectonic. The engine sequence, heat source, either radiogenic or primordial, creates a hot core and mantle, which is transferred outward primarily by mantle convection. Convection generates mechanical force on the rigid lithosphere. Then this force drives plate tectonic. You can see from heat that is within the mantle and core, it now through convection, that is energy transfer, it comes onto the plates, which is the continent, then forming tectonic activity, which eventually results to earthquake and all that. The two the two layer system, earth convection is likely layered. The whole mantle convection, the dual mantle convection. The whole mantle convection, subduction slab or slabs may sink to the core mantle boundary. While in dual layer, the mantle may convect in two layers, separated by about this 660 layer driving plates. The ultimate driver without this internal heat engine, plate tectonics will grind to a halt. The surface will be a static, dead world. Now, what does this mean in bits? In bits. Oh, sorry. So now, this ground unification, again, meaning that what I've summarized here, I decided to make it in bits again, in pieces. Think of the Earth as a massive heat engine. This is described as the ground unification. The way internal heat translates into physical movement of the continent. We shall break this down into source, the transmission, and the results. So the engine sequence from heat to motion, like I said earlier, from heat to motion, heat flow, mantle convection, then plate tectonic. From heat, that's where we have the source. This is the fuel. It comes from primordial heat. Leftover heat from the Earth violent formation and regenerating heat. The constant decay of elements like uranium, which you saw in the previous granite example. The mantle convection, but that's how this heat from the core, from the mantle, is transferred. Because the mantle is hot and under pressure, it behaves like a very thick fluid over millions of years. Hotter, less dense rock rises while cooler, dense rock sinks. This creates a circular conveyor belt motion. So you can see it keep moving. When it's hot, it moves up, the cool one gets down. So heat is being transferred up to the outer mantle, to the crust. Then this movement of Earth, as the mantle moves horizontally under the crust, that is the lithosphere, it acts like a friction-driven belt, dragging the tectonic plates along with it. Driving plate tectonics. I mean, so the convection cells dictate what happens at the surface. Upswelling, downswelling. Upswelling forms ridges and rifting. Downswelling causes subduction and pollution. These are all activities resulting from plate tectonics. So you know what this is. The two-layer system, how deep does it go? Geologists are still debating exactly how these conveyor belts are organized. There are two main theories of it: the whole mantle convection, the entire mantle from the crust all the way down to the core mantle boundary, stays in one big swoop. That means the motion is not gradual, everything moves. The dual convection is the mantle is stratified, layered, where there is a shallow loop in the upper mantle and a separate slower loop in the lower mantle. So look at this example here. This is mantle. This is the loop I'm talking about. So meaning that the whole, everything of the mantle keep revolving, keep revolving. But when it is dual, it moves such that the upper one moves first, it turns then before the lower one now move. Okay. The most important takeaway for your for exams for this example, for um the most important take from this is that heat is life, geologically speaking. With heat, we have volcanoes, mountain building, and magnetic field that protect our atmosphere. Without it, convection loops, convection stops, the plate stops moving, and the heat becomes a geological dead world. much like Mars or the moon. So geologically, those are dead, planets. Nothing happens there. So this is just another example of the motion that I explained. Oh, I think I'm done said. To summary, heat is the currency of global geological dynamics. We have quantified its source, transfer, and measurement. Geothermometry allows us to decipher ancient thermal conditions, providing a time capsule of the engine's past states. Mantle convection is the link between abstract heat flow and tangible theory of plate tectonics. Broader implication, the engine also powers the geodynamo, generating a magnetic shield, control long-term climate via volcanic outgassing, and also concentrate the mineral resources upon which modern society depends. Final thought is to understand the face of the earth, you must first understand its fairy interior. So these are, as usual, example, calculation, example, calculation, example, calculation. So let me, for this course now, you have your CA next week. You have the one for, what's it called now? What's that called? 3211. That will be maybe around 4 this evening. So you have the CA for this one. Next week, next week, wait. Please, what's the population of this class? Class rep, I don't know if you are here. If you can hear me.
Good morning, sir.
About so about 50 something, like 50.
Send me an Excel sheet of name and matric number of everybody.
Okay, sir.
In the Excel sheet.
Okay, sir.
As soon as possible. All right. So let me allow you to go and prepare for your test, okay? Or any question? All right. See you later in the day.
Recording stopped.